So anyway, today we're going to talk about polygons. A polygon is nothing more than a closed figure in a plane. So if you look below, I have examples of polygons, not polygons. So the biggest thing what I want you to understand is if you look at this one, this is a closed figure in a plane. What's the difference though? Because this is not a polygon and these are. So what's the difference? They have straight edges, right? Okay, so obviously then that throws out that because that's got a curved edge. This isn't a closed figure. This is a closed figure, but it's got some antennas, so that doesn't count. How come this last one here isn't a polygon? It's two figures. Okay, so a polygon is nothing more than a closed figure in a plane. It's made up of segments. So now we're just going to talk a little bit about terminology. I don't know if you need to write this down because chances are you probably already know it. The sides of the polygon are just segments. Okay, I have those pointed. They are in pink. Okay, so the sides would be, there's three of them there, and then the vertex, vertices is plural of vertex, those are just the points. Okay, now another term that we use, consecutive angles. What does consecutive mean? Consecutive. When you think about consecutive integers,
Two things that are close together.
they're close together. How close together are they?
Very close.
They're the closest together they can be. So consecutive means next to. So consecutive angles would be angles next to each other. Consecutive vertices, vertices next to each other. And consecutive sides next to each other. So consecutive means right next to. So now, in your book, they have a chart that lists all of the different sides of the polygon and what that special polygon is called. You already know most of these. You know a triangle, a quadrilateral, pentagon, okay, 5-sided figure, hexagon, 6-sided figure, heptagon. You will hear that referred to like the heptathlon is 7 events in the Olympics. Octagon. They said that octomom, remember she had 8 babies? Okay, nonagon, decagon, like the decathlon in the Olympics, which has 10 events. The undecagon, I've also heard this referred to as the, I've heard it referred to as another one. I can't remember what it is off the top of my head. Okay, the 12-side figure is a dodecagon. And then if you just have a number of sides, you don't know, like, you know, like, oops, hit the wrong one, just a second. Like if you had 25 sides, we would call that a 25-gon. If you had a 100-side figure, that would be a 100-gon. So here's a little bit about how we name polygons. How we name polygons is we name them in this case, alphabetical order. We could also name this as pentagon A, E, D, C, B. So you see how we kind of go around in a circle? We could also name this B, A, E, D, C. Okay, generally it's the most acceptable way to use it alphabetically if you can, but those other ones are acceptable as well. So we would call that pentagon. There's not a nifty little symbol for pentagon. We have to write the word out. But if you look at the one below with the triangle, that one does have a nifty little symbol. Okay, just a small triangle. And that would be triangle ABC. Remember, we could also call that triangle ACB. We could call it triangle BAC. All right? So now, let's go ahead and look at what we have next. We have the diagonal of a polygon. This is something that the diagram speaks volumes. Okay, the diagram speaks volumes more as to what it is as opposed to the definition. The definition of the diagonal of a polygon is a segment that connects two non-consecutive vertices. It connects two non-consecutive vertices. Now in that figure, that's a diagonal. Do I also have another diagonal? Yeah. I have another diagonal that goes right here. Okay. So if I were to pick another shape, let's just go with a, I don't know, let's try a hexagon. Okay, let's just try that. I'm going to fill it up real quick with white so we can use the diagonals a little bit better. So let's talk about diagonals here. If I start at this point, I have one diagonal here. I have one diagonal here. Do I have any more diagonals from that point?
No.
Yeah, down
Oh.
here.
Just from
So there's 3 diagonals from that point. If I start at the top point, I can't go here, that's consecutive. So I go down here, that's 1. Then I go down to the bottom. Then I go here. Can't go here. So then the next one. Let's start over here on the right. Right here. I can't go here because I've already gone there with the purple. So I can go down here. And then I can go down here. Let's go over here to this one right here. I can't go to the blue, can't go to the purple, but I can go straight across right here. So if you notice, every vertex has how many diagonals attached to it? 3. But some of them are shared. So that's what diagonals are. Let's go ahead and look at the next one. This one is defined as being convex polygons. And so what I'm going to do is I'm going to give you a handout right now, and you're going to use this handout later with an investigation. But what it does is it gives examples of convex polygons and concave polygons. And so if you want to make notes on here for your own information, that probably would be a good idea. But if you notice a convex polygon, if you were to draw all of the diagonals in, all the diagonals will be on the inside. Okay, so if you draw all the diagonals in on those convex polygons, they're all going to be on the inside. Now, if you look at the concave polygons, if you draw diagonals, you've got one or more of them outside. So that's a formal definition of a convex and a concave. What I want you to do right now is look at your examples I gave you of convex and concave. And I want you to tell me another thing that you observe. Because instead of the formal definition, there's another way to tell me if it's convex or concave. What do you notice? Yep.
The convex are all polygons, or like regular
Okay.
shapes.
So they kind of look like shapes that you already know. There's one specific thing I'm looking at that concave does that convex don't do.
concave goes in.
Concave goes in, so kind of if you think about it, think about an indentation or a cave. You know how a cave kind of goes inside the side of a mountain? Think about that way. So a concave polygon looks like it's kind of got a cave in there. So that would be another way that you could do that visually without having to draw the diagonals in. Otherwise, if you draw the diagonals in on the concave, you will get one or more of them outside, and that will make it concave. Alrighty. So, real quick, we're just going to talk about this. This is something that is one of those things that should make sense. It says if polygons are congruent, then corresponding sides and angles are congruent. So basically it means if they're the same, if they're congruent, they're the same size, then the angles should be the same and the sides should be the same. Likewise, if you know that all the corresponding sides and angles are congruent, you can conclude that the polygons are congruent. And so down here below, what we have is we have 2 polygons. And we're going to look at their markings to determine how we write that they are congruent. If you look at the first one, I'm going to call that CAMP. So then I'm going to put my congruent symbol. And then what I'm going to do is I'm going to look at and I'm going to see C corresponds to what angle in my second polygon? S. So if C is written first, S is written first. Okay. The next one, A. What does A correspond to? I. Okay, now in order to see if it corresponds to, remember you look at the tick marks. M has 3 tick marks. T has 3 tick marks. And then last but not least, E and P are left over. Now there is another way. If I would have said P, M, A, C, what would that correlate to?
Yeah.
E, because P goes with E, T goes with M, I goes with A, and S goes with C. So you can write it in numerous ways. All right, so here you go. You got your expressions handy. You got your expressions, turn them on. I want you to go ahead and, let me go ahead and move this over, and let me go ahead and move this out of the way. I need you to go ahead and tell me what polygon is congruent to A, B, C, D. And the answer is B. Nice job. So the best way to do that is to look for the tick marks, which I think most of you did. Okay? You saw that A would have correlated to J, N, and S. And then you look, A is between two single tick marks, S is between two singles, N is between two singles, J is not, so that automatically eliminates J. Then the other big difference, you know that none of the angles are marked in C, so that throws that out. Your answer has to be B. Okay? So a perimeter of a polygon equals the sum of the lengths of the sides. You should already know about perimeter. You've discussed perimeter over and over and over again.
You don't have to write that down.
Okay, yeah, I mean that's something that, to me, you should know about perimeter. Perimeter is the sum of the lengths of the sides. So now, this is how confident I am that you know perimeter. I want you to tell me what the perimeter of that figure is. There's actually a shortcut way for how you can determine that. And the perimeter is 37, nice. The one I was talking about, the shortcut, you know 5 and 5 is 10. So you add 15 and 12, you know that's 27. You add your 10 and you get 37. Okay? So special polygons, this is what I gave you. On your sheet, you have equilaterals, not equilaterals. You have equiangular, not equiangular. You have regular, not regular. Your task for the rest of the period is to come up with definitions for equiangular, equilateral, and regular based on what they have given. Okay, so if you look at the first one, and for sake of time, we're going to kind of go through and do this together. Okay, for sake of time, let's look at equilateral. What do you notice about equilateral? Yep.
All sides are the same.
All sides are the same. So equilateral polygons, polygons in which all sides have equal lengths. So you can either put this in your definition sheet, or you can write this on your sheet that you were given there. You can throw this in with your definitions. Equilateral polygons are polygons in which all sides are equal. All sides have equal length. Okay. So your next one is equiangular. Equiangular. All angles are in fact equal as well. Okay. Equiangular are polygons in which all angles have equal measures. And that should make sense because equiangular, equal angle. And last but not least, a regular polygon. What can you tell me? Polygons that are both equilateral and equiangular. So if you want to talk about something that kind of simplifies things, you could have said all sides are equal and all angles are equal. That would have worked. Or you could say they're equilateral, which we know means all sides, and equiangular, which means all angles. Okay. Now that is it for lesson 1-4.
We don't have to do the ones on
So now that is it for lesson 1-4. So for your assignment, here you go, 1 through 18. 21, and 22, and that's found on pages 56 and 57. So 56 and 57, 1 through 18, 21 and 22. Now, in looking at this last night, or actually yesterday afternoon, okay, hopefully this shouldn't take you longer than a half an hour to 45 minutes, if that.
So it
It
takes
should
longer
go
than we
very
won't do it,
quick.
right?
So.
What is it with you